So welcome everyone to the seminar today. It's my pleasure to introduce Kristina Monakhova. Kristina is visiting us from Cornell, where she's assistant professor. She did her PhD at UC Berkeley, working with Laura Waller, and then a postdoc with Sixian Yu at MIT. And now she's building up a group in computational imaging. As I understand, she's been working a lot on low light imaging. She has some great work in the past on extremely low light imaging, very challenging scenarios, and looking forward to what she has to say. So please join me in giving Kristina a warm welcome.
Thanks so much for having me here. Really excited to be here, tell you about some of my work. So just to get started, overall, I work on imaging systems, and there's billions of cameras around the world, and everyone uses cameras. We use them to take selfies, we use them for science, we use them to image black holes and for medical diagnostics. And overall, this area of computational imaging is we want to make cameras and microscopes and telescopes that are more capable. And you can do this, as I'm sure you've all seen, through this co-design of the optics and algorithms, where if you think about these things together and not as separate components, you can optimize the optics together with the algorithms to do more than 2D, to do things like 3D from a single shot. You can see fast motion, you can see polarization, hyperspectral information, phase. You also make your camera really compact and small and lightweight. I have some PhD work on this. But then also, perhaps you want to see in extreme low light, and you want to see in the dark, or you want to see in signal-starved regimes with microscopy, where you just do not have so much signal to go by, but you want to extract as much information as you can to make interesting discoveries from your imaging systems. So today I'll talk about two projects that I worked on kind of this low light regime for my PhD and for my postdoc work. So the first one focuses on photography and trying to see in extremely low light scenarios, and by learning kind of a better noise model to represent noise in very low light situations. And the second one is work for my postdoc, where I'll talk about how some of those ideas apply in microscopy and how we can try to make some of our algorithms more trustworthy for scientists to use by adding uncertainty to them and then using this uncertainty in the loop to have an adaptive acquisition that's much faster than you could before. So, okay, that's the overview of the talk. Let me dive right into the first project. So the best cameras on the market today, or at least a few years ago, whenever I did this project, need at least moonlight illumination to capture motion at night. And if the moon is not out, you have to have a much longer exposure time. And so this precludes the capture of motion. And so if you want to, see what animals are doing in the darkest nights, you're under a dense tree canopy whenever it's cloudy. If you have a passive CMOS sensor, you really can't do it so well today. And so generally, cameras are really good whenever there's a lot of photons. So they're good in daylight all the way through kind of quarter moonlight. And even your iPhone might do pretty okay in an urban environment at night, but it will not do so well in starlight, where there's no moon and you have really tiny amounts of light in the scene. And so the goal of this project was to push this and show photorealistic videography at starlight. And so, okay, how do you go about this if you want to push the cameras to their limits and see in the extreme dark? Well, first you need a really good camera. And then you can take these kind of high gain videos and somehow apply some sort of algorithms perhaps to get back some nice photorealistic denoised videos. So the first question is, what's a good camera for nighttime videography? What do you need in order to see in the dark? Any ideas? Feel free to shout it out. What sorts of things do you care about if it's really, really dark? If you want to capture as much light as possible?
Large aperture.
Large aperture, yes. What else?
Exposure time.
So you can have a longer exposure time, but we want to see videos, right? So we want to see motion. So hopefully we can try to bring that down as much as we can. But overall, a larger exposure time works. Yeah.
More sensitivity to light.
More sensitivity to light. So you need kind of a better camera that's more sensitive. Yeah. So these are all correct. So we want to capture as much light as possible. So we want to have really large pixels that will capture as much light in the scene as possible. You want an aperture to also capture as much light as possible. And it turns out, one surprising fact is that if you care about imaging in starlight, you actually really need near infrared sensitivity, because if the moon is out, you have a lot of light in the visible regime, but if the moon is not out, if you're under starlight, there is a lot more light in the near infrared actually. So if you're a little bit sensitive to that, it could help. Well, luckily, Canon has a camera that satisfies all of these requirements. It has huge pixels. We can buy a very good lens, and you can have this modified Bayer pattern that actually has IR sensitivity in every single color channel. So you try to maximize how much light you get while still getting a color image. Okay, so we got one of these cameras. And now the question is, how well does it do with no algorithms? Do we need any algorithms at all to solve this problem? But to do this, we want to go somewhere really, really dark. And here's a light pollution map of Boston where I did my postdoc. And as you can see, there's a lot of light pollution. So if you want to see in these sub-millilux levels under starlight, you're actually not anywhere close to there. You're somewhere around 20 to 50 lux, not anywhere close to sub-millilux. And so you want to go somewhere, you could do this in a lab, you can turn off all the lights and do this, but we want to have compelling videos under starlight. So I had to go somewhere a little bit more remote, and I did this project whenever I was doing my PhD in Berkeley, and there it's a little bit more sparse, and you can drive out a couple of hours to a place where there's very, very little light. So we did that and collected a bunch of videos under whenever it was a moonlit, clear night. And we had this very expensive light sensor that verified that, indeed it was between 0.6 and 0.7 millilux. And we took a whole bunch of videos at 5 to 10 frames per second. And as a baseline, I had my DSLR camera with me, and I took a 30-second exposure, and that's what I saw. But now we want to take, 5 to 10 frames per second videos and actually see motion and see some signal in them. So if we do this with our fancy camera, you actually, can we turn the lights off, by the way? Okay, so you can see a little bit, right? So this is the raw data from this camera, and you can see some motion, but it's very dim. So if we contrast stretch it, you can see a little bit of something, but you also, if you zoom in, you see a lot of structured noise. But this gives us a lot of hope. If we can somehow get rid of this noise and extract the signal, we can actually achieve our goal and have photorealistic videos in sub-millilux. But now, how do we do this? We need a really good denoiser. And we have a lot of options in denoising. This has been around for many decades, and we can choose an off-the-shelf denoiser perhaps and see how well it does. So in the scale of denoising, I say there's kind of classic methods and then deep learning-based methods. And classic methods usually don't need any training data, they just work off the shelf. But unfortunately, if we apply kind of a classic method on our approach, like VBM40, you can see that we still get all of these streaks and a lot of the signal is gone. And our noise is highly non-Gaussian. And so a lot of these denoisers have been kind of designed assuming Gaussian noise, and they totally fail on our real data. So alternatively, we can do some sort of unsupervised method like noise to self, but because we have this correlated noise and these line patterns, it ends up thinking this is actually signal and doesn't do so well either. If we go to kind of the other extreme, we can say, well, what if we had some data? What if we could collect our own data set from our camera? We could take some high gain, short exposure images, and then some low gain, long exposure, noiseless images, and train something from scratch. We train a denoising network based on these pairs, and then we could, kind of learn the network parameters and get the best denoiser for our given camera. But if you think about this extremely low light scenario, if you do frame by frame denoising, you miss a lot of information because there's correlations across time. You know that tree is still there, so you should use this because that signal isn't going to change so much. So if you do frame by frame denoising, it's going to result in a lot of flickering and a lot of loss of details in your scene. But, okay, can we extend this to do video denoising? And this is computationally impractical because if you collect a real data set of noisy and noiseless videos on your camera, they will not be motion aligned. So this is just experimentally impractical, cannot quite do this. So instead we said, okay, let's try kind of this middle ground approach of simulation supervised learning, which means that, perhaps if we just had, just some noiseless videos, either from online or from our own camera, if we had a really, really good noise model, we can synthesize noisy videos, train a denoiser from those, and then hopefully this would work on real data from our system. But, what's a good noise model? And our noise isn't Gaussian. So if you use a Gaussian noise model, it clearly does not match the real noise. And if we try to hand calibrate our noise model with kind of the best low light noise models off the shelf, it also doesn't quite fit our noise profile. So if you use this, it's not going to work. So instead what we said is, okay, let's use some data and try to learn a noise model. So you can collect a data set of still images of no motion, where you just take a burst of high gain, short exposure, noisy frames, and some long gain, long exposure, noiseless frames. This is a calibration process you can do kind of maybe even at the factory, for example, for your camera. And then we want to use this to learn this noise generator, which goes from a clean image to a synthetic noisy image. But the problem is that if you take just a pixel-wise loss, it doesn't quite work because noise is stochastic. So you can assume that every time a different noisy frame will have slightly different noise. And so a pixel-wise loss will have a different value. You cannot quite minimize this sort of function. So we said, okay, let's replace this loss with kind of a discriminator. This is all before the rise of diffusion models, which I'm sure you can also use for this. But so we decided to use a GAN for this project and said, okay, we're going to have this discriminator try to kind of learn this distribution of fake noise versus real noise. So then, you train this in an adversarial setup, you have your noise model create synthetic noise, and your discriminator say this is real or fake. Hopefully these converge, and you get something that produces synthetic noise that's indistinguishable from your real noise. But, GANs hallucinate, they're hard to train. And so we constrained our noise model with a few physics-based noise parameters that we know about low light noise. For example, if you read a textbook on kind of noise you might see in high gain settings for CMOS sensors, you have a couple of parameters. For example, you might see this read and shock noise, which is parameterized by the standard deviation of this. So there's two parameters here. You might have this random offset noise that's added to your columns, and that's also just single parameter here. So we have this kind of low dimensional model of what the noise could be. So we only had to learn a few parameters. Then we correct for any errors in this model. The CNN, which also learn at the same time. So this constricts the search space and allows our model to converge most of the time and give us something that looks, rather than like Gaussian noise or like this hand calibrated model, something that looks very much like the true noise from our system. So okay, to summarize, now we have really good noise model. We can take clean videos and pass them through and generate synthetic noisy clips. But now, this is only half the problem. We really want to denoise these and make sure that our denoiser still works on real data from our system. So we train a denoiser with these synthetic clips using videos from online, which are just RGB. Remember, our camera is not RGB. It has this near infrared channel, so it's actually surprising this works at all. And so we pre-train with these RGB videos. We fine-tune a little bit with some noiseless clips from our own camera, as well as some noisy still pairs from our camera as well, just throwing as much data as we can to this problem. And whenever we do this, here's what we see. Here's a still image. That's the raw noisy clip. If we do the standard classic method, you get all these line artifacts. If you do an off-the-shelf deep method, it's blurry. You still have a lot of line artifacts. If you train a single image denoiser with our own data, it does a lot better, clearly. But then ours, which uses multiple frames, has even more detail. You can see a lot more detail in the text of this book, and it closely resembles the ground truth image here. But the real test is how well does our denoiser do on this? On real noisy image videos from our camera. When we took this, you couldn't see your hand in front of your face. It was so dark. There's no lights. There's only the stars, and it's extremely dim that you really just cannot see anything at all. And if you contrast stretch these videos, you see a little bit more. With a classic method, there's a lot of flickering, there's a lot of lines. With a single image method, there's a lot of flickering. With a deep method, it's all blurred out. And then finally, with ours, we see, well, I don't know if you can see this from my angle, you can't see this at all. Okay, you can kind of see this a little bit. You see all of this detail. So we're actually able to see these flags blowing in the wind. We're able to see some of the details on this cactus. And if you look closely here, whenever this video replays, we actually can see a shooting star going across the sky. There it goes. And we can see these slow-moving satellites going across the night sky as well. So our frame rate is fast enough to capture these fast dynamics, these shooting stars, and we maintain enough detail to see these slow-moving satellites going across the night sky. Here's a kind of a compilation. Here's another noisy clip, and here's a compilation of some of the denoised videos where you can see the Milky Way in the background of this person playing volleyball. You can capture people dancing, and these people can't see anything. They're just kind of dancing blind. And the person playing volleyball actually dropped the volleyball about 2 frames after this because he couldn't see it. And so now we have something that's not quite perfect cinematography quality videos, but we see a lot of signal, and we're able to really do this by saying, okay, let's take our camera and let's use data to calibrate it. So we have a model, a noise model that's specific to this camera at the highest gain settings, where it's perhaps nonlinear, where there's effects you cannot easily model, but we can learn it from data. And then you can use this learned model to train a denoiser and use synthetic clips and really push the limits of your imaging system. Of course, it's not perfect. It only works for a specific camera gain. And you could imagine setting this to work for a camera at any setting, but then you might have to think about thermal effects and other factors, but perhaps that's possible as well. And maybe photography isn't so exciting, but what if you could do this for astronomy, for microscopy? There's a lot of applications where this could be really important. And one day we hope that the image quality will be so great that it's going to be a new show on Netflix about animals at night. But we're not quite there yet. Okay, so that's the first project. And now some of my more recent work is saying, well, can we use some of those same ideas in microscopy? But there's some problems. And the first is as follows. Carl Sagan said that every time a scientific paper presents a bit of data, it's accompanied by an error bar, a quiet but insistent reminder that no knowledge is perfect or complete. However, a lot of times these days, whenever we do computational imaging, we may have some sort of perhaps a deep learning based method as our algorithm, and these do not give you an error bar. So you say to the doctor, this is the image, but which part should they trust? Should they really trust these images? Should they trust all parts of the images equally? And so it'd be great if you could have some sort of error bar to kind of assess how good your performance is or how much you should trust it. The other thing is that a lot of times deep learning based methods will have hallucinations. They'll hallucinate, which are these realistic looking artifacts that are not truly present in the sample. Here's an example from MRI where this is what the algorithm gives you, but this is the ground truth. And so, to our eye, this looks like it's plausible, looks realistic, but really it is not there. This is all hallucinated. And so if you want to use this to, diagnose someone, it'd be great if you can know, which regions you should trust and which ones may be a little bit more uncertain. Okay, and so, if we want to, use this, we want to somehow make these algorithms more trustworthy for our scientific imaging. And okay, so to do that, we're going to do kind of two things in the second part of this talk. The first is I'm going to show you how you can add an error bar to any arbitrary supervised learning reconstruction. So if you're using like a CNN or something like this, you can use this method. You can add an error bar and have some notion of uncertainty. And then we are going to use this notion of uncertainty to drive adaptive acquisition, so that if you can rescan your sample, you can rescan just the most uncertain regions, and then try to build up this confidence over time and reduce overall uncertainty in your estimate. And we're going to do this for scanning microscopy, which is really common in biological research. So there's different types. There's confocal, two-photon, multi-photon. But essentially what you do is you have a system that scans point by point all of the points in a 2D or a 3D sample. And sometimes the sample might be moving. It has interesting 3D structures. Maybe it's actually, your microscope could be planted on a mouse that's actually moving around and has a pulse. And this becomes very challenging. But we're going to assume that, for now, we're going to assume you have just a 2D sample that's just scanned, and we want to do something a little bit better. So in these systems, there's a trade-off. If you use a really high-power laser and you stay at each point for a long time on average, you can get great image quality. However, each time you shine this pulsed high-power laser at your sample, you damage it, and at some point you kill it. And also, this is really slow. So if you have a large field of view, or if you want to scan in 3D, this is going to take a very, very long time, and maybe your sample is going to move during that time. On the flip side, if you have a lower power laser or a shorter dwell time, so you stay at each point for just a small amount of time, you get much worse image quality, but a lot less sample damage, and you can go really, really fast. So we say, okay, this is a denoising problem. Can we, do this much faster, but then use algorithms to try to recover more information? And as before, you can say, all right, we're going to take noisy measurements, have a denoiser, denoise your images. And it helps if you have not just one image, but perhaps if you have, a burst of images, because this will help you get better image quality potentially. But now what we care about is to say, if we use a denoiser, do we trust it? Where do we trust it? And so we want some notion of kind of the uncertainty at each point in our recovered image. And generally, the way this has been done in the past using deep learning is to say, perhaps we'll use Bayesian dropout. So you can do a whole bunch of forward passes through your network, each time dropping different random weights. And each image is going to be a little bit different. And if you do this enough times, you can have a per pixel probability of what the intensity should be. The other common technique is an ensemble method where you actually just train a whole bunch of different networks. You run your image through all of these, get a bunch of different answers, compare them, and get this pixel-wise uncertainty. But, as you might imagine, these are very computationally intensive. And do we trust them? Is this actually giving us uncertainty, or is it something else? So recently, there's been a new method proposed, which we leverage in this work, which is based on something called quantile regression and conformal risk control. And rather than giving you this per pixel distribution, what you get is a per pixel bound. You get an upper bound and a lower bound, for the intensity in that image. And the way this works is that you basically, normally you might have, say, a mean squared error or a sort of loss between your ground truth and your image prediction. But now we're going to have a different loss called a quantile loss. And you're going to not just predict one image, but 3 images, your image, your lower bound, and your upper bound. So how does this work? Well, mean squared error is a symmetric loss. So if your prediction is too big or too small, it doesn't matter, you have the same loss. It's going to drive your image towards the mean. Quantile loss, or pinball loss, can be asymmetric. It has this tuning factor alpha. So if alpha is small, you have this asymmetric sort of loss. So if your prediction is too big, you'll have this positive error and a larger scaling on the loss. And so this is going to drive something to be an underestimate or a kind of a lower bound. And the opposite is true. If your alpha is big, you're going to encourage something to be larger than the mean due to this loss. So, okay, we have these 2 different asymmetric losses. One will give you the lower bound, one will give you the upper bound. And so after you train the network the same way you would any other network, you basically will get an upper bound and a lower bound. This is really fast. That's great. But do we trust it? Is it actually the uncertainty? And that's actually the next part, is we say, all right, so we're going to have 2 steps. We're going to train this new loss, and then we're going to calibrate it. So we have a held out data set of calibration images, which could be from our own data set or from something else. If you want to switch this task to say, I trained on images of people dancing, and I want to apply this to microscopy images, you can say, I'm going to calibrate with the microscopy images. And what you do is you say, I'm simply going to rescale these bounds until, say, 90% of all the true pixels lie within those bounds, which you know from your ground truth. So you simply just scale the bounds bigger or smaller until you have the desired coverage, which is user specified. So you can say, I want 90% coverage, or if I want to be even more certain, you can say 99% coverage. If I care about less, you can say 80% coverage. So okay, you basically pre-train this network, which has a lower bound and upper bound. You calibrate those bounds, and then you can automatically predict uncertainty. It's really fast, and it has actual guarantees that in expectation, as long as your data that you test on is similar in distribution to your calibration data set, that this will indeed cover, say, 90% of the true pixels in your data set. Okay, so let's try this out. So we did this for multi-image denoising for a scanning microscope. And if you pass in this noisy measurement and you denoise it, you also get this heat map of uncertainty, which is just the upper bound minus the lower bound. You can see that certain regions are more uncertain, more red than others, which are blue. And if you do multi-image denoising, if you pass in 2 images, or I guess this is 3 images, or 6 images, you can see that the uncertainty goes down. And so we go from being something that's very uncertain, very red, to something that's a lot more certain and converges to this sharp denoised image with a lot of fine features. So yes, go ahead.
So is this notion of uncertainty related to variance or to signal to noise ratio?
It's also related to kind of the features in your image, so it depends on the model. So it's kind of learned from the model here. You can see, you're right that this is a system with Poisson noise, and you can see that you have higher uncertainty where you have more signal here. And whenever you converge, that's still true, and you will still have kind of higher regions of uncertainty where there is signal, but the overall uncertainty goes down, and so it shouldn't go to 0. But it should be related to the variance.
Okay, variance, right? Because Poisson noise, yeah, if it's brighter, you will have higher variance, but the signal to noise ratio is also higher.
So I would say it's related to the variance. Okay, so the thing that's really interesting here, though, is if we zoom into a region here, you can see that this is the measurement that we have. It's very noisy. Here is the denoise prediction. Here's the uncertainty. Here's the ground truth. So our model predicted there's a little loop here. If you look at the ground truth, there's no loop there. So this is an example of a hallucination. And our uncertainty map, shows this is very red, and it's highly uncertain. And if you go through this and add more data to it, you have 3 images, 10, 20, this loop disappears. It goes from being there. If you look at the cyan arrow, it disappears after 3 and 10 images. It's totally gone. And uncertainty also goes down in that region. So you can use this to help you perhaps find places where your model is a little bit less trustworthy, and you can collect more data and hopefully try to limit the hallucinations we have in your model. And this also works on other systems. So we train this with kind of these online 2-photon images. We tried it with this home-built multi-photon data set, which it has a lot of idiosyncrasies and weird types of noise in it. But even with this sort of system, you can see that overall you can pinpoint these areas of high uncertainty, and this uncertainty goes down. And also here's a region where there's hallucination. It predicted there is this dark feature here which isn't present in the ground truth. And with more rescanning, both the hallucination disappears and our uncertainty goes down as well. So we can help find regions where there may be hallucinations in the prediction. But the really exciting thing is to say, well, can we actually use this in the loop to drive kind of a better scanning process? We don't want to rescan the whole field of view every single time just to collect like random samples of the object. We want to do this kind of in a more clever way. And so we say, okay, let's do this uncertainty-driven adaptive acquisition, where you denoise, predict the uncertainty, threshold the uncertainty, and then rescan just the most uncertain regions. This way, you can save on the total light dose to your sample. You can do less damage to your sample, and you can sample just the regions that are challenging for your denoiser, the regions where it's not so confident. And so if you try this on some real samples, you actually get these kind of adaptive masks, and you can sample, say, 11% of the total pixels, depending on the density of your sample, or 36% for a more dense sample. And so it's actually kind of automatically segments regions of interest in our samples, and we'll just focus in on those and collect more data on those points. But if you do this, non-adaptive versus this adaptive approach, it performs, fairly similarly and is able to eliminate the hallucination in both cases. And so you're able to really kind of pinpoint in on the regions that you should rescan just those regions, and get back a much better prediction of your image and reduce the uncertainty overall. Okay, so I showed you here in the second half of the talk 2 things. The first is how you take some supervised machine learning approach and add error bars to it using conformal risk control, where you now have an error bar for each pixel, and then you have a second calibration step where you calibrate these bounds. And this is really fast. It's much faster than the Bayesian methods or the ensemble methods. And it has real guarantees that if you're imaging things that are similar in distribution to what you calibrated on, in expectation, these bounds should hold. And if you have a pre-trained network that does this, or it gives you these bounds, you can just calibrate with a tiny data set of, say 10 to 20 images, and have these bounds hold on those new images. Then we propose this new method of, saying if we have uncertainty, let's use it. Let's drive adaptive acquisition using uncertainty to have something that's both algorithm and sample informed. And in simulation, we're able to show that this could get you up to, say, 10x less light dose to your sample, which could be really important for microscopy. The big limitation of this is that we collected real data, but we didn't do adaptive scanning in the loop. And that's one of the big next steps of this project, is to say, okay, let's actually have a random access microscope. Let's have all of this in real time, and let's rescan adaptively a sample. But there are a lot of problems that, we assumed static, non-moving samples. People usually care a lot more about dynamic 3D samples. And so some big open questions and next steps is saying, can this work for 3D? Can this work if there's motion? And then also, I get this question a lot is, well, how do you trust your uncertainty? And, overall, I think that having some notion of uncertainty is better than not having a notion of uncertainty. And even if you can't trust it, maybe it's better than not having it at all. But so trying to make sure that this is something that scientists can eventually use and leverage, and something that's actually helpful for them is another big future step. So, okay, that summarizes these two projects. And overall, I think it's really exciting trying to kind of push the limits of what we can see in extreme low light through better data-driven models of our sensors, but do this in a way that's trustworthy and robust, and perhaps even adaptive based on this notion of uncertainty. All of this work was done during my PhD and my postdoc, but now I want to give a quick plug to my new lab at Cornell, where we're continuing some of this work and doing some new work on this co-design of optics, algorithms, and high-level tasks to make better imaging systems for lots of different applications. That's the conclusion of my talk. I'm happy to take any questions.
Maybe I can start off, and then we'll go. Because I wanted to ask about this uncertainty, and maybe this gets to Kiros' point, but I guess there are different sources of uncertainty in the system, right? There's the statistical uncertainty, which I guess you call aleatoric uncertainty, and then there's the uncertainty in the model itself, which would be epistemic uncertainty. And the latter would be from the training data, right? Because the model is saying, given what I've seen, similar patches, neighborhoods, these pixel values, this is my upper bounds, my lower bounds, this is my mean, I guess. So in this framework of I guess, what is it called, formal risk control, is there any way to disentangle these sources of uncertainty, or no?
Not as far as I'm aware, so they will be entangled. And so you have kind of a simplistic notion of the uncertainty. So, maybe with the Bayesian approach, you might have the actual distribution, or maybe if it's binodal, you might have multiple peaks or something like that. Here, you don't get any notion of that. All you get is a bound. And hypothetically, all the uncertainty in your system should be in that bound, both from the data, both from the model.
Yeah. Good.
But I think that's maybe what you want. I'm not sure.
Yeah, maybe.
Yeah, my question was also related to the uncertainty quantification. So it seemed that a lot of the results, the uncertainty maps, seem to be around edges. Do you think this uncertainty is derived from the specific input, there's actually noise around those locations, or do you think it's because the network is, do you think there's a bias in the network itself that's causing it to produce uncertainty, larger, I guess, upper bound and lower bound ranges around these regions?
So I haven't seen it so much around edges as regions where there's high intensity. So there's definitely a correlation between the intensity and the uncertainty that it sees. But you can think of it that if you're looking at something and something is background, there's probably nothing there you don't care about necessarily. And if there's a place where there's a lot of signal, there's something there, but you don't know what it is. And so this model is trying to kind of find these regions and say, okay, there's something here, we need some more data, and if we have a little bit more data, the uncertainty goes down because we now have enough data to know what that is. But but it's definitely still correlated with signal, and it never goes down to zero. It'll always, but it's also like very closely resembles kind of the variance you might expect in a signal based on Poisson noise. And so there are some relations to that as well.
If you change the architecture of the network, do the results change or?
We've tried several different ones and they're pretty consistent.
Okay.
They all have slightly different bounds. They're not identical, but you'll still see similar features.
I see, that makes sense, thank you.
Yeah, so I guess going back to this issue of uncertainty and adaptive imaging, it seems a bit counterintuitive to me that you will first go and re-examine parts that have already received a lot of light or that are very bright. So for example, with Poisson noise, the variance goes to zero when you have no photons. But do you have no photons because there's nothing interesting or because you have simply not received enough light there to actually figure out what it is?
That's a really good point. I also do think that if you take a close look at these noisy images, you can see that there's something there, but the true structure is unknown to us. And so that's kind of why we focus on those, or why I think this focuses on those regions, is because the model, thinks, there's most likely something there. But if you look here, with our data prior from all of the images it sees, it's likely there's not much there. Could we miss something? Absolutely, we could miss something with this. And so, but I think that if the goal is to kind of find the most prominent signals in the system, then this will do that. And I think a lot of times there is a lot of background, especially in microscopy, and perhaps you don't care about some of those dimmer regions anyways. You care about kind of the regions where you have the most photons, the most fluorescence.
Yeah, I guess maybe that regime is special in that case. It seems to me that often you care about improving data where the signal to noise ratio is low. So in the case where you have this, like at the Poisson at least, you may have more variance, but also the signal is higher. And so that's actually more certain than areas where you have fewer, you have.
But so I think there's a difference here. I think if you're thinking about photography and you want to say, I want to go back to my initial example and, try to make the dimmest things have more signal. So if we go back to like this image here, yeah, perhaps you want to, have more signal here in these dim regions and really build this up. I think that's not the case in fluorescence microscopy, where what happens is,
yes.
What you care about is the background should be dark, and we tag certain things. They fluoresce. And we want to find those regions where there's like a lot of fluorescence, a lot of things that are happening. Those will give us some structural information about where the cells are, where things are co-located. And so there, you really care about those regions and trying to get them as accurately as you can to make sure the structure is accurate. And the darker regions are just background where we don't care what the background is. So it's not quite like photography. I think it's a little bit different in that case. Sampling the regions with higher intensity, where it's more likely there is an interesting signal, is a little bit more advantageous.
So I guess that you'd apply the framework, like if you were to apply the framework to you're using a different notion of uncertainty. Right?
Yeah, I think you wouldn't want to use the same notion of uncertainty for photography.
Is it a global scaling for the balance? Like when you do the recalibration?
Yes, so that's a great question. So in this work that I'm showing here, this is indeed a global scaling because you have 3 different images. We have some other work, which I don't show here, where we say this doesn't have to be a global scaling. Perhaps you can actually modify your network so that this quantile percentage is an input, and then you can actually have the scaling be based on that. And so you might have not something that's pixel-wide scaling, but it depends on the scene context. You might scale certain regions more than others. So we've tried that as well. For microscopy, for like point-to-point scanning, it seems like it still does more or less a global scaling.
I think if it's a global scaling, can't I just pick any arbitrary image and always rescale them so there's 90% coverage?
What do you mean?
Like, I can always generate 2 random images, scale them to the upper and lower bounds of that 90% of the
Well, so
intensity
yeah,
size
of course
and
you
go
can
down.
say that, if my image is limited between 0 and 1 intensity, and if I have a bound that goes to 0 and something goes to 1, you're going to cover 100% of it. But the goal here is to say I want the tightest bound such that it still covers the right fraction of pixels.
Can you capture that notion of tightest bound here?
Yes. Well, so the work this is based off of quantify kind of what the tightest bound is, how close this gets to it, and we're building this off of this. So I would say that we haven't looked so much into it, but it's based off of work that does have this tightest bound. And I think I'm sure you can go tighter, but then it depends on how good your model is. It depends on your data, how much data you have. But of course, you want to go as tight as possible. Because if you have a bound that's just huge, it doesn't tell you anything.
Other questions? Yeah, here and then.
So my question was about noise, like in the first work, when it generated noise. Like how sensitive is to hyperparameters what the final model that you get is?
So we don't have, well, we learn all the parameters from the data. So if we go back to this, so like all of these parameters are learned automatically from the data. So we don't tune these.
Yeah, okay.
There are a lot of hyperparameters in machine learning in general, like learning rates and things like that. And those are all something that could affect it. So you want something that converges.
Andrew, and then over here.
Yeah, I also had a question about the noise model here. So I see you have all these physics constraint parameters like fixed pattern, rate, and shot noise. Why is there also do you find the need for adding add a CNN as well? And what type of noise is that supposed to model?
Yeah, that's a great question. And so, overall, if you can have like a parametric model where all the sources of noise in your system, you should do that. We found that adding CNN helped, which means that we didn't get everything correct. And in particular, we have this, Gaussian read and shot noise model. This should be Poisson. At the time, we didn't have a way to do a differential Poisson model. And so we had this approximation, and that could be one source of error. In practice, what we saw is that adding the CNN changed the distribution, kind of scaled it down a little bit. And overall, what you care about is kind of how accurate your distribution is to the real noise. And so it played some role in helping us match the distribution. And so I think it's partially the approximations, maybe there's something else it was doing, but overall, if we did not include this term, it didn't perform as well.
Esther, and then.
Great talk, as usual. I have a question about the resolution. If you train on, let's say, a 4x downsample of images, and you get an uncertainty map, would that uncertainty map be the same as if you train on the full res images, but then downsample the uncertainty maps? Because the idea there is you can potentially, in the adaptive scheme, use a smaller or larger field of view lens, but then a smaller NA, and then you can do a sparse scanning with coarser detail, and then get the uncertainty and then start honing it, get a progressive level of detail in your adaptive scheme as well.
Yeah. So we haven't tried this with multiple resolutions, but we have found collaborators who can do exactly that in hardware. And so it is possible to try exactly that idea, and that's one of our future directions.
I have two questions. One is that, by the way, great talk. So in the noise modeling, you have the part that you're saying is physics informed, and then you have the CNN because you're saying some parts you're not able to capture. But then CNN can also mess up all the noise that you've added previously. Did you try to bake that into the CNN to not touch those values, like a gauge equivariance sort of CNN that would not touch the modeling of the noise that you already have, like the read and shot noise and the row noise you have? Like somehow bake it into the CNN. Don't touch these, just add extra amount of noise, and then also you can study that noise and see what exactly that is.
So in practice, we don't separate it out during the training. We don't say like, okay, we're going to like learn these parameters first, or calibrate these parameters, and then add the CNN. We do this all like end to end. So the parameters and the CNN are learned together at the same time. And so what that means is that like, are they physically meaningful still? Maybe not.
It could also be that some of the like read and shot noise is being I don't know, disentangled into two parts. Like one part is actually the read and shot noise that you were informed to learn, and the other part is being learned by the CNN.
It could be. Yeah, so we don't do anything to make sure that these are separate.
Yeah, so that was one thing. And another thing was that you said your alpha hyperparameter was 0.05 and 0.95, if I'm not mistaken, for the lower and upper bound. And it seems like that gives the impression of you chose those values because the difference of those is 90%.
Yeah, that's right.
However, you do a scaling afterwards, with, let's say with 20 calibration images.
Mhm.
And I think, did you try, just out of curiosity I'm asking, did you try different values of alpha to see maybe you can find the tighter bounds for, like you don't need to scale quite as much when you're doing your calibration? Because like that alpha is not necessarily, the difference between those two alphas being 90% isn't necessarily translated into your uncertainty being 90%, right? So did you try like different alphas to maybe get a tighter band?
So yeah, this is a really interesting point, and it's the fact that if you want to aim for 90%, you might say in training we can choose these alphas to be like 0.05 and 0.95, but do we really get this? It's unclear, and then you have to add this calibration part. We've since moved on to doing kind of a slightly different model of this, where you predict a single image and you feed in this alpha into the network. So whenever you train all values between 0 and 1. And then during the calibration, you can say, okay, I'm going to start off with 0.05, 0.95, and then you can actually scale the input network until you have the right bound. And then you might end up being 0.02, might end up being something else. But so yeah, this is all really interesting, and you can couple them a little bit tighter by doing slightly modified version of this training.
Like an expensive way of doing this comes to my mind is like doing a gradient-based hyperparameter optimization for alpha to see what would be the best possible alpha you could put in there, but that's probably expensive.
Yeah, but so if during training, rather than predicting the lower bound, upper bound together at the same time, you can say, I'm going to say, if I feed in like alpha is 0.01, I'll give you like the lower bound and have that be the loss, have just this one loss that can change. Right. Then you can do this all together and have one network that can predict any quantile. And that ends up being a little bit more powerful. And so then you don't have to do all of this.
Yeah.
Okay, maybe just one last. Did you have a question, Kira?
For the sort of dancing of the stars work, did you notice any difference in performance between modeling the noise of the mosaic versus raw images?
So let's see. So we did like a very crude demosaicing where we just split it into 4 channels. And so that's like all the comparisons are based on that. So we didn't do any sort of like demosaicing other than just splitting into 4 channels.
I see.
And then we just added the noise to that directly.
And the near IR, did that affect things much in the end? Did you have a near IR channel here?
Yes. So whenever I show this, I'm showing the RGB channels. Actually, so if you want to actually get back like a colored image, you have to subtract out the IR channel. But if NIR is all you have and you subtract it out, suddenly you're left with nothing. Which is why you see that for an image like this, you see color, and for the rest of our results, you don't see so much color. And so these are all coupled. Maybe you could somehow get back the color, but right here I'm just showing kind of like the RGB channels, and you don't see color so well.
Actually, near IR it's not exactly just an IR cutoff. It actually has a pretty significant response. Like it has a an IR bump, but then it also has another bump in the red, I think.
Yeah, so our sensor, I can actually show you, our sensor itself had a response that looked like this, where it's sensitive
Right.
here. So like each color channel, like blue, has another, bump in IR, which is why you could, take this IR channel and subtract it from the others to get that color. But then in Starlight, you just don't have much data. And so a lot of the stuff that's in blue, green, and red is the IR. And so, at some point we were talking about, oh, let's hallucinate the colors, try to like recolor it. But that's something that you could do potentially.
Okay, well, maybe if there are other questions, we can take these offline. Kristina will be around. We'll have a reception right after this, just out in the DGP kitchen. And yeah, if we can thank our speaker again.